Hi. It's recording, yes. Can you hear us?
Yes.
Yes, okay. Yeah, let's continue. I guess there's no problem. So in this study, when you have these trade-offs, so parameters to study, then you cannot do for each choice of these parameters for these trade-offs carry out in a subjective study. That's not possible. So you have to either use some existing data set to analyze these trade-offs, or you have to use a simulation study that does not rely on subjective tests that you have carried out before. So both of these approaches are contained in this work. And then the next question is the criteria to study this trade-off. And there are two criteria that were involved here, namely the goodness of fit in the form of the so-called G-test that is familiar to many of you, I think, and then the root mean square difference between reconstructed or synthetic ground truth distortion rate functions. Okay. No, wrong button. No?
Sorry.
Now it should work again. Yes. So before we can go into the technical details about the trade-off studies and how the methods, how the analysis was set up, I have to review how the ASC3 methodology works, because that's needed to understand the technique. So here just a quick overview of what the projects and JPEGs were just a few months ago. They have updated this picture online, I saw last night. So JPEG is a working group of ISO and ISC collaborating with ITU, and ASC is just a small sub-project there. And ASC stands for Advanced Image Coding and Evaluation for the first and the second part of ASC. And in the third part, and that is the part that is relevant here, subjective quality assessment of high-fidelity images, we changed the meaning of the AIC abbreviation to assessment of image coding, because the project does not involve research in the coding methods themselves, but only in the evaluation of the performance. So it's assessment of image coding. So we focus on coding artifacts and leave out other artifacts like camera defects or issues in the illumination in the environment and so on. So I reported about this already last year at VQuack a couple of times, and in the meantime on February 9th, this standard with the number of 29170-3 of our part 3 was published, and so it's there. And also an example implementation for the data analysis is ready, and it's publicly available on GitLab at this link. Okay, and currently we're working on the fourth part of JPEG, or the preparation of it. It's not yet started. And that will be on objective image quality assessment for this high quality range. And so for this, we have our ASC data set that we collected in part 3, and we will also collect a new data set, ASC4, which will be larger, containing many more sources. And we'll hear about that in the next session in the talk of Mohsen. But now it's about ASC3. So as I mentioned, ASC3 focuses on the very high quality range of image compression. So on the MOS scale, say from 4 to 5, and it's a fine-grained scale. So we want to be, we want to have a high accuracy and a high precision in this high range. And there was a previous effort in ASC, that's ASC2 part 2, the flicker test, which can decide whether an image compressed is visually lossless or is lossy. And now we want to vary that in order to come up with a scalar number which reliably classifies, not classifies, but quantifies the strength of the perceived distortion in this range. So that will be the J&D scale from 0 for lossless, mathematically lossless compression, 1 J&D where 75% of the participants can reliably recognize the image between the reference and the distorted image. The one that is distorted, they can identify it with 75% probability. That's 1 J&D. Okay, there were no data sets in this range available, and so we had to create one. And these images were collected by JPEG ASC a long time ago, like 3 or 4 years ago already, and those were used in ASC3 for this study. We had these 6 codecs that are listed there from JPEG to JPEG AI. 10 bit rates were used for each of the codecs and each of the sources. And so we have 5 sources and 300 distorted images altogether. So the goal was to assign a quality value to all of those 300 distorted images. And in particular, not just the numbers, but functions that are distortion rate functions. So we are given the bit rate of the corresponding image, and then the function calculates the estimated perceived distortion on the J&D scale. And this was a lot of work for the crowdsourcing that had to be split into 3 campaigns over a year, and we collected 560,000 responses altogether, including those that we had to reject because of lacking reliability. Okay, so now let's go into the subjective assessment scheme of ASC. So it's by comparison. Which image has the stronger distortion when we compare 2 images side by side, and the reference image should also be visible in some form. So for plain triplet comparisons, we have the 2 compressed images, and the source image is maybe in the middle, or in our final decision that we made, it is behind the compressed images, and the user can toggle the view between the originals and the compressed images. And the boosting then is applied to the compressed images, and we have several boosting mechanisms there. There's artifact amplification, there's a flicker, and also zooming. Then for the display of the boosted triplet comparisons, we are asking which of the 2 versions, or which of the 2 compressed images, when they're flickering with the reference image, has a stronger flicker effect. That would identify the one with a higher distortion. And now for this talk here, we have to look at budget allocation between the same and cross-codec comparisons, or the trade-off there. How to divide the budget between these different versions of questions, same and cross-codec comparisons, and also plain and boosted comparisons. And then in the next talk, it'll be an ablation study for the joint modeling. We have to model or calculate the distortion of the plane stimuli, the compressed plane stimuli, and not of the boosted stimuli at the end, and so the data has to be merged somehow in a model, and then we have also the functional model, namely the distortion rate functions, and both of those can be handled together or individually, and it was not clear until now which of these 2 measures would be the stronger one, and how much of an advantage it makes to have them both together. Okay, so for a triplet comparison, so as I said, there's 2 distorted images, and then when you press the Show Original button here, these two images go away, and behind it there are the undistorted images, the reference images. And then you can press it again, or then you can press it again, and then you see the distorted images. And users are required to at least look at the originals once, and they can look at it multiple times, and they cannot press this button more than 2 times per second. Otherwise, it would be like a flicker effect. But we limited it to a minimum of 500 milliseconds, before you can press the button again. Okay, and then the question is which image has a stronger distortion, left, right, and also we have a not sure button in the middle, and to reduce the mental stress that occurs when images are almost equal and they have a hard time figuring it out. And then for the boosted triplet comparison, so we have the zooming, so this is a zoomed version of this flower. And we have artifact amplification pixel-wise. The differences are multiplied by a factor of 2, and we have zoom and we have flicker. But so now you don't see any flicker, or the flicker is so small that you don't see it. So then you would say, okay, I'm not sure, and maybe okay, now it doesn't. It should flicker. No, it does not. It did in my keynote, but oh yeah, this is a PDF now. That doesn't flicker. Okay, yeah. So the intention was that this one flickers and this one has invisible flicker, and then you would say the left flickers more. Okay, yeah. All right. So now, when you have collected the data, you have to reconstruct it, and this is the process of the reconstruction. So we're aiming at these distortion rate functions where the independent variable is the bit rate and the dependent variable is the perceived distortion in J&D units. So we have these functions. So for a small bit rate, we have a high perceived distortion, and then when the bit rate goes higher and higher, at some point it will be lossless, and then the distortion will be 0. Okay. So now when we have a cross-codec comparison, and this is the case, so we have like a red codec and a blue codec, let's call it that way. So we sample the red codec here at 1 bit per second and the blue codec at 2.5 bits per second. And then on the perceived scale, we get these two distortions of 0.4 and 0.95 JNDs. And then the Thurstonian model that we use will say, okay, you'll put the Gaussian around this on the vertical axis, and then with these two Gaussians, you subtract these random variables, and then the result will be 1 Gaussian, and then from that you can read off the probability that a user will give the correct answer when comparing these two images in the plain triplet comparison mode. Okay, so this is the possibility, but then we have also the boosted versions of it. So the boosting then effectively applies a boosting transformation that maps the perceived distortion to a new scale, the boosted distortion, also on the J&D scale. This is also perceptual. And so there we have the same variance for the Gaussians, but the numbers here are higher than here. So 1 JND gets boosted, in this case, very strongly to 4 JNDs, and here 0.4 gets boosted to 2.8 JNDs. Ignore the minus signs here, they have no meaning. Okay, so the overall mathematical model consists not of quality values themselves, but of distortion rate functions and these boosting transform functions. And we have used polynomial functions here of degree 1, 2, or 3. And for these functions, we have tried functions from different families, exponential families, logistic family, polynomial families, and so on. Okay. All right. With this setup, of course, then maximum likelihood can be applied, because everything is, this is a probabilistic model after all. And then with the maximum likelihood estimation, we come up with the distortion rate functions for each source codec pair. And this is an example result for our source, the nighttime scene. And here we have about 500 triplet comparisons, so the questions for the 6 codecs and this source image. with these 10 levels of distortion, and 15,000 responses went into the reconstruction of these curves. And so each dot here corresponds to the image, and on the vertical axis you see the calculated or the estimated distortion in J&D units, and these all are functions from the exponential family. So it's a one parameter, a factor times the exponential, and then there's a linear function of the bit rate R, of course, with a negative sign here, because these functions have to be monotonically decreasing. And the transfer function from a perceived distortion for the plane stimuli to the boosted distortions, that's a T of D, is a quadratic function here. And typically you see that the quadratic coefficient here is a negative number, with one exception. Okay, so this is what comes out, and for every source. Okay, now we come to the main part of the presentation, and namely the trade-off study. How should you do this if you have to? Okay, so we have a budget constraint. So let's say we have 1,000 euros or so, or dollars, for a crowdsourcing study, and now we want to decide how to divide it up between the sources and between the different types of questions. Okay, so we have two parameters. As I said, we have to study the ratio of plane versus boosted triplet comparisons, and Q, the ratio of same versus cross-codec triplet comparisons. Okay, so like a two-dimensional search space now. And we have the two methods using the data from the crowdsourcing campaign that we have, and I showed you an example of it on the last slide. And method B would be simulations, only pure simulations from a mathematical model of ASC3 type, so using formulas similar to those that were shown on the slide before. And then we have the G-test for goodness of fit or root mean square error for the reconstructions as evaluation criteria. Okay, so maybe here one remark, just quickly. So the budget that we have, of course, is in terms of dollars or euros or so. It's fixed, and one has to take into account that the cost for the different types of questions is not the same. A boosted or a question with a boosted methodology is much cheaper. You can do it in half the time than a question with where you manually toggle the view and plane triplet comparisons. So in our ASC3 experiment, we found out that there's a factor of 2 there in terms of the cost. The PTC comparison costs twice as much as a BTC. So if you have this, then and the parameter P of PTC is 0, then we have zero PTC, but 2,000 boosted triplet comparisons for a budget that would buy us 1,000 plane triplet comparisons, right? 1,000 plane triplet comparisons can buy you 2,000 boosted. Now, when you change this ratio P here, then you get these curves, the blue curve and the red curve for the number of triplet comparisons of each kind, PTC or BTC. Okay, so when the ratio, goes up, the total number of comparisons decreases from 2,000 to 1,000, and these are the formulas, and you can easily check that. Okay, so here's an example. Like if we have our budget N of 1,000 plane triplet comparisons and have a ratio of 0.25 for plane triplet comparisons and 0.6 for boosted triplet for cross-coded comparisons, then this table here on the right comes out, and the 4 numbers in this 2x2 matrix then gives you those 4 numbers of comparisons or responses that we can collect given the budget and these parameters. And now as you change P and Q, which we have to do in order to find the best possible implementation, then these 4 numbers will change in the table. Okay. So, the question is for a given budget N, which PQ gives the best reconstructions of perceived distortion magnitude? Okay, so for the trade-off analysis, we have to define how we can sample the BTC, PTC responses and how to define the ground truth. Okay, so let us assume a fixed configuration of image sources, codecs, distortion levels, compressed images with and without boosting. So the data set is fixed. Let's think about such a scenario. And we also, of course, fix the same in cross-codec questions. So then we have a collection of questions that we can, for which we have to assign numbers of responses, and we know, the images and all the codecs and so on. It's all there. Otherwise, it becomes way more complex. So this is the first thing that one can do with a trade-off analysis. Fix as many parameters as are reasonable to fix. So now we have two ways to assess the sample. If we are working with a large data set, and we have one with the 500,000 responses, or we can use simulations from a functional model. That is, we just hallucinate these exponential functions for 6, 7 codecs and one source, and then we have a ground truth from it. And the ground truth can be thought of in two ways. Either we say the response ratios in the empirical data set, or the response ratios coming out of the mathematical model. That's the ground truth. And then we should use the goodness of fit. That's the natural statistical approach to assess the goodness of fit and the success of the method. And when we look at the distortion rate functions and try to assess the difference to the ground truth, then the ground truth for the empirical approach would be the reconstructed distortion rate functions from the entire data set or from a reasonably large subset. And for the simulation, we don't have a problem at all. In the simulation, these distortion rate functions are an integral part of the definition of the model. So the ground truth is explicitly given. There's no question about it. Okay, and then the accuracy would be a difference, a root mean square difference in the first case to this reconstructed version, or the root mean square error for the simulation case. Okay, this is how the method works in practice, how to set up the system. So for the empirical data set, we start up with a list of questions, and we have all the responses in the data set, and then we sample it according to our budget and to the parameters P and Q. So then we get out a new set of responses R prime, but for the same questions, and reconstruct a mathematical model using a maximum likelihood estimation. So we have the model M, and the questions are passed through also. And then we can extract the response frequencies from the model, from the reconstructed model, and the given questions. And then we have the expected frequencies of all of the responses. So for each question, how many say left, how many say right? The not sures are split 50-50 always in the data set. And then the ground truth then comes directly from our data set, and the response ratios are there, and then we can see what is the expected number or the observed number of responses, OI, and from EI and OI, you just look up the formula for the g-test. That's all that is needed, and then you calculate it and come up with the goodness of with the g-test value. Okay. Now, if we use a synthetic functional model, it is very similar. So now we don't have data, but we have a model, but we have the same questions Q in here, and now we can just sample from this model. We have the distortion rate functions, we know the bit rates and so on from the questions, and then we get a set of responses R for those questions. We can reconstruct as before, we can extract the response frequencies as before, and for the ground truth here, there's one step here. We have to extract the response frequencies that are not explicitly in the model, but implicitly. You can calculate that, of course, easily, and then we get EI and OI, and again, compute the g-test value. Okay, so a couple of remarks now in red. Okay, for the first case, for the empirical data set, there is a bias in the ground truth if the ground truth, or if the data set is not large enough, if it's not fully representative of the population. Okay, and for the synthetic functional model, there's also a possible bias in the ground truth, namely when the null hypothesis that is in this model here, the model implements just the null hypothesis, or we assume that the real world behaves as in the model M, and but the null hypothesis should be or is imprecise in general, right? So we have this also for the ASC3 data set. We applied this modeling technique, reconstructed it with maximum likelihood estimation, and then we looked at the results, and the model cannot explain all of the answers to, not the answers of all of the questions. And that was the content of my talk last time in December at the QUAC. Okay, so there's also a ground truth bias in the null hypothesis. Okay. Just one other remark. The g-test is nice to have from the previous slide because it's consistent with the optimization by maximum likelihood estimation. G-test essentially is equivalent to negative log likelihood. It's just a difference of negative log likelihoods scaled. And so optimizing MLE or the g-test is equivalent. So that is very nice, a nice consistent framework, while if you have to work with a oh no, the g-test is here. Okay, if you have to work with a root mean square error, then there's a break in the methodologies between the maximum likelihood estimation and then evaluating with the root mean square difference. Okay, so how does it work with the root mean square difference? Very similar now to what we have before. So for the data set, we sample it, we reconstruct the maximum likelihood model, and then we have the maximum likelihood estimation, and we have a model M, and we get the same procedure for the entire big data set, and then we have a model M star, which we regard as the ground truth, and then we can compute the root mean square difference. And we can compute it for different quantities, for the plain stimuli, or for the boosted stimuli, or for both together. It's not quite clear what one should use here. Okay, and for the synthetic model, it's similar. Of course, we have a model now, ground truth model M star. We sample it, we get the responses, reconstruct our model from the small sample, and then in the ground truth, we have the model M star. And then we can compute the error between M and M star. And M star is the true ground truth, except for this inherent model error because the null hypothesis might not be fitting the entire population. Okay. Okay, as I already marked, the root mean square difference is not consistent with the optimization by MLE. That's a little bit of a taste. Okay, so now we come to the results. So using the data set here, so the gray shaded stuff I had already explained. And now after cleansing the data set of the 560,000 responses, there are 320,000 left. And then for the functional model, we use the exponential one with quadratic boosting functions as shown in the example slide a little time back. Okay, and here you can see in the table the number of questions that we had for same codec, cross codec, plain triplet comparison, boosted triplet comparisons. And then the number of responses per question, we had 50 responses, more or less, for plain triplet comparisons, and for the boosted, we had a lot more, 100. Okay, and here are two papers where you can look up some details about it. It was presented before also. Now, there are some limitations in the data set. It says imbalanced, and I would like to make sure to explain what type of imbalance I mean here, namely for some questions, like the trap questions, there are many more responses that were collected. In the upper left histogram, you see that we have, for some questions, we have 600 responses, and for others we have 200 responses, and for most we have around 100 responses. Okay, so this is a little bit of an imbalance in the data set. Alleviate this problem, we have reduced it, or we have resampled it so that we have 100 responses from PTC and from boosted triplet comparison questions, and 50 from plain triplet comparisons. Another issue is the oversampling. So here you have the PQ plane, and so for a large P or for a large Q, you have to have a lot of cross-codec comparisons. And in our data set, we did not have a lot of cross-codec comparisons, maybe only 9% or so. And that means if the Q is too large, if we are asking for a subset that requires more cross-codec comparisons than what we have in the data set, we have an oversampling issue. We are no longer getting in more information, but we are just repeating information that was already there. So it's a bit of fake news. Okay, so there are some limitations, and like this blue curve here is the upper boundary for in the PQ plane for this particular setting that we had initially, and so that had to be addressed here in this study. Okay, so as I mentioned, we have resampled the data set to make all the numbers of responses equal for BTC, and for BTC it was 100, and for PTC it was 50. On the next slide, I can show you that the ground truth is not much different in most of the cases. And okay, and in our simulation study, we used 7-bit rates for PTC and BTC, and not the 5 and 10-bit rates that we had in the empirical data set for consistency. And the oversampling issue was solved by by our natural restriction of the budget that allows only for about 6,000 responses per source. And so there, oversampling is happening only near P and Q, both above 0.5. Okay, so here you can see the differences when you reconstruct from the full data set or from the data set that has the same number of responses per question type. And this is a difference in root mean. This is a root mean square difference, and for the 30 cases of distortion rate functions. So for all the sources and all the 6 codecs, and you see it's on the order of 0.1 or less J&D, so very small. So I think also without this stratification, we would get very similar results. Now, this is the result for the G-test. Here we have parameter P, parameter Q going from 0.1 to 0.6. So here, the red curve there is the parameter line where above it you have the oversampling issue. You would have to sample more cross-codec responses than there are available in the data set. The lower part here is the one that we can trust more than the upper part. And the color shading is so that the lighter colors, the yellow colors, have a smaller G-test value, and that is better, closer to 0, which would be the best. And so here for this, in this experiment, we see, okay, the minimal G-test was obtained there at the upper right corner, around 0.15 ratio of plain triplet comparisons and 60% cross-codec comparisons. And yeah, the results are noisy, and so we had to average over 250 reconstructions for each of the 5 sources, and yeah, 50 trials per source. That's 250 reconstructions. Okay, that is the result for that. And now for the root mean square errors. So here we have the same experiment with the other objective criterion for PTC and BTC. So here is this is the mean now of the root mean square differences for PTC and BTC. And we have now optimal trade-offs, different parameters, 0.25 and of plain triplet comparisons and 20% cross-codec. And again, this is from many realizations averaged. And if you split this up between PTC and BTC, you have these two diagrams. So this is the root mean square error for plain triplet comparison. So for the original unboosted stimuli, and here you find that for a larger ratio of plane triplet comparisons, you have the optimum here, and here it is for a smaller one, and that seems to be expected, because here we have like 10% plane triplet comparisons and 90% boosted triplet comparisons, and here we are looking at the boosted triplet comparison, the performance on that, and there for PTC, and so the point is further to the right. Okay. And we also computed the standard deviation, and the standard deviation for these g-tests, for the root mean square error here in this case, is almost as large as the root mean square error by itself. So it's quite noisy. All right, now we come to the second part with the simulations. So now we are hypothesizing that the crowd workers behave like the mathematical model that we have. So for example, we take one source image, it doesn't matter which one, it's abstract anyway, and we hallucinate 7 codecs, C1 to C7, and they all work according to the exponential model with these 2 functional parameters. And for the boosting transformation, we take a degree 2 polynomial like that. Okay, so now the samples for the responses are drawn from these binary random variables that we derive from the models, and no longer from the empirical data set. Okay, and the ground truth for the root mean square error computation is given by the distortion rate function of the models, by these functions here, or the parameters are given here, and not by the reconstruction of from the data, the large-scale data. This is a slide that explains in detail how to divide up the responses to the different categories. It is technical, and I included here. You can read it up in the slides that are then put online here. So now just the results. So we have the mean of the g-test for this simulation. Now we can have a larger range of p-values here and q-values there. So from 0.1 to 0.9, and we see that the optimum is obtained averaging over 200 trials here at like 40–50% plane triplet comparisons and 60–70% cross-codec comparisons. Okay, and when we look at the root mean square error, we have similar pictures as before. So for the error of plane triplet comparisons, we have a ratio of 60–70% plane triplet comparison, and if we want to look only at the boosted root mean square errors, then it is 0.1 is better than 0.5 there. Okay. Now, if we look at the mean of the root mean square error for both plane and triplet and boosted comparison, so taking the overall accuracy, then we have, again, something in the middle of the road, like 20–30% plane triplet comparisons and 50% cross-codec comparison. That would be the best. Okay, so now I'll come to the summary and then to the last slide, the conclusion. So we discussed 4 methods to study the trade-off of choices for the distribution of questions and numbers of responses for the assessment of perceived distortion magnitude using ASC3 data sets. So we can use either the data set, or we can have a synthetic model, and then we can use either the g-test or the root mean square difference or the root mean square error. So how flexible are the methods? So if we have a data set, we are restricted. The data set is limited, and so our search space is limited, and we don't have as much freedom as with a synthetic model. There we are unlimited, no limits. We can try any ratio of P and Q. Okay, and also draw as many samples as we like. And the samples can be as large as we like. So these are all things that are not possible with the original data set. So the resources that are required for these approaches are, well, with crowdsourcing, it costs time and money. Okay, if you have not already done a crowdsourcing study, you will probably not do one just to figure out this trade-off. And here we have just pure simulation with the model. It just costs compute time, and you have to implement it, of course, but this is not so hard given the given the data analysis software that is available. So there are some biases there in the ground truth and other problems. So in small data sets, we have a bias, or here we have a bias in the distortion rate functions when we look at the root mean square errors, and we don't quite know whether we should focus just on the plain triple comparisons or on the performance of plain and boosted triple comparisons, and it's inconsistent with the maximum likelihood estimation. And the other parts are consistent with the maximum likelihood estimation. Oh, this should be consistent, not inconsistent. I have to correct that. And so there could be, however, a bias in the null hypothesis. But okay, that's the bias that we have to deal with in any case, because that's also what we do when we reconstruct from the data that we eventually will assess. Okay. Oh no, the inconsistency is because of the root mean square error. So that's correct. That's correct. So sorry. Okay. So finally, conclusion and limits. So my personal choice is the simulation with synthetic functional model and the goodness of fit. It has maximum flexibility. It does not cost any time and money for a large data set. It's fully consistent with the reconstruction method of models from data. It's easy to implement. The only thing that's a problem is that it does not yet perfectly fit the data. So when we have models that are a little better or much better even, then that will go away. The limitations are, okay, we consider the trade-off only in the 4 categories of questions. But we didn't look at what happens if we extend the number of questions, ask more questions or fewer questions, and then, we can reassign the number of responses for the different questions. Or we could also consider one question with 100 responses, another question with 200 responses, if we liked so. So the search space is, it's infinite. But yeah, one cannot do everything, but it would be worthwhile to also study that, like how many or what type of same-coded questions should one ask, and what types of cross-coded comparisons should one ask, and there are different options. Okay, so then the assumption of distortion rate functions that we have intrinsic in the model, it may fail for some codecs. So codecs are, the traditional codecs like JPEG, they have one quality parameter, and as you scale it up, things are quite smooth. But modern learning-based methods are not of this type. Maybe there are learned models in there for different bit rates, and then when you go from one model to the next, there's a jump. It's not a continuous distortion rate function anymore. So that means that these functions, an exponential function or a power function, so might not be the best way to proceed. So for this case, one could just return just to pointwise reconstructions. So this is something that we have already observed, for the JPEG AI codec, that for some codecs or for some sources, there was a strange behavior in these functions, or also in the pointwise reconstructions. Okay, and then, of course, as I said, here we have to work on the modeling to improve the functional joint modeling a little more. Okay, so I think that was the last one. Thank you very much for your attention.
Are there any questions?
Thank you. I can pass them. Any questions for Dietmar, online or in the room?
No? Okay.
I have 2 questions. So one is you used in the data, you used kind of limited number of sources. Did you do an analysis just for one source and for another source and see how much it differ? I'm wondering if this could influence.
We have done the study per source and then accumulated the results in these graphs. So these are averages over all the sources and all the codecs. So this is 5 sources, 6 codecs. So for distortion rate functions, we have 30 of them. And then for each we have a root mean square error, and that's all averaged in this here. So yes, the performance will be different. And there was one page where, well, not near this one here, that also shows you a little bit of that effect. So here we have the difference between the reconstructions from the very full data set or from the small sample in the data set. And you can see the dependence on the different sources here. So for for JPEG, source 2 has an RMSE for 0.13, but for the others it's much smaller. So there is a source dependency, of course. And yeah, we have a night scene in there, and a natural scene, and a noisy one, or something. Yeah, they are different, and give us different performance numbers.
But it's not a huge one.
No, in this case, and I think also for the others, it's not very huge. But as I said, for JPEG AI, we have a significantly, visually, very significantly different reconstruction, both in terms of pointwise and boosted. So, for example, the boosting did not increase the distortion, but decrease the distortion, it seems, from the data here. So this was unexpected, but it's averaged in there now. Yeah. So this is why I said at the end that we have to look at the details of for each source codec comparison or each source codec case. Does the functional model work well? Does the pointwise model work? Maybe does it give very different results? And if so, well, how can we interpret that?
Thank you very much. And one another question, you previously showed a model, it's the page 12. There were some plots. I didn't fully understood here. Those points are the points that you are selecting. It's not from the data, yeah? This would be impossible that it fits so perfectly, yeah?
No, the bit rates are from the points. So we have for each source codec comparison, so here we have six curves, one curve for each codec, it's the same source, that one up there on the left. And so we have 10 images for this source and the JPEG AI codec down here. And then our result is that we have for JPEG AI here, this is the distortion rate function for the JPEG AI, and this is the blue curve. It's an exponential curve. And we say the result of ASC3 reconstruction is that if you want to evaluate the quality at the given bit rates, it's just at these points. Okay. Yeah. If you were to, if you use the ACR scheme or something, or just the pointwise reconstruction, the points would not be on a smooth line. They would be a bit noisy, and maybe for JPEG AI there would be 1 point way down here, so, for example. Yeah.
Thank you very much. There is a question. Could someone pass the microphone back to Alex?
Yeah, thank you. Really very interesting work. Has there ever been feedback, if I understood it correctly, that also, also boosting of the same areas in the non-distorted images would have been somehow helpful? Probably not, right? I mean, because one could imagine that you can better judge the distortion, because I understood correctly that the boosting didn't affect the original image, right?
We have compared always the undistorted original source image with the compressed image, which has distortion, for the plain triplet comparisons. And for the boosted, we amplified the differences between the compressed and the source.
Okay.
And globally over the entire image, not focused on where the distortion is large. It's a global thing. And so we amplified with a factor of 2 the differences in RGB channels. And we had to clip, because if an R value is above 255, then it's not reasonable. So we clip it to 255. And we make sure that this clipping does not occur too often. So 2, 3, 4% of the pixels might be clipped a little bit. And okay, but then besides the amplification, there's also the flicker, which also enhances sensitivity, and the zooming, the spatial zooming. But recently we came to the conclusion that maybe the zooming is not necessary or should be avoided, because we are blending out some details of the background that might be important. And so now in the next study that we do, we will only use the artifact amplification and the flicker, but not the zooming.
Thank you so much. Yeah.
I have online question, if that's first time.
Please go ahead.
Thank you, Dietmar, for the talk. We have both did some simulation and some analysis with a bit different way. But from your last remark, Dietmar, about that to use the pointwise reconstruction instead of the rate distortion function to fit function like this, I think for generalizability, this is better, because we need to estimate the distortion for wider range of distortion that are not included in subjective tests. And also, you need to train a model that mathematical model or benchmark tune mathematical model or existing IQ metric or learning-based codec to predict the quality for unseen model. Unseen image. So it's probably the rate distortion function that we have here is more generalizable in that case. Even I understand that for some learning-based codec, as we will also discuss in next presentation, that they might be not really monotonic and relevant to the rate distortion and rate distortion function.
Yes. Yes, can I comment here?
Yeah, please. Yeah.
So yes, yeah, you're right. Of course, if you use just the pointwise reconstruction, then it is not clear how to interpolate between the points if you want to assess the quality for unseen stimuli. That is true. Well, when you have the distortion rate functions, the functions are defined over the whole real line, and you can evaluate it at any point. Yes.
Yeah, I expected also it will be more generalizable for real, and also in the reconstruction that you showed in one of the previous speaker meetings, that the point was reconstruction. It was very close to the point that estimated with the rate for the rate distortion function.
Yes, they are very close generally, and in fact, in the software that does the that does the reconstruction for the MLE to assess the functional models, the starting would be the version of the functional model that comes from the regression of the pointwise model. So I do first the reconstruction of the pointwise model, then I regress a functional model to the data, which is very simple, a nonlinear regression, and then from that point on, it goes into the nonlinear optimization to find the parameters of the functional model, the parameters of the exponential function, and the parameters of the boosting transfer function.
Yeah, so that's it. Yeah, thank you. Another comment is about the amplification. We did not do clipping, Dietmar. This amplification between two, it was the objective with most of the pixel, they will get these two amplification. But if it's going to amplification to be clipping, result in clipping in one of the channel, we reduce the amplification between 1 and 2 until we don't have clipping. So we avoided any kind of a clipping in the value.
I think we did clip, but okay, let's not discuss it here. Yeah, you can explain it to me when I'm back in Konstanz.
Yeah, thank you. And also about the simulation can be extended, at least the way I did that. You can also look to if this distortion function that we assume that with a very large number of the data it can be estimated, for example, exponential. If we have a small sample of the data and we have this joint model, again, it would suggest the same function as the base function that fits the data or not. This is what also I have in other simulation. So it can be expanded in this simulation in many dimension and to look to different data. Thank you very much. Was good talk.
Thank you.
So thank you very much. Are there any other questions? Or actually, even if there are, I would prefer to move them offline because we've got a second presentation by Dietmar, and I will just switch the slides.
Yeah, this will be shorter, so I think yeah, we will be on time, hopefully. Yeah, that's the ones. Okay, so can you go to presentation mode? Yep. Okay, so this is the second part of this afternoon session, and it is closely related to the first part here. So again, we are looking at the modeling as I explained at the beginning of the last talk, and so now we have these distortion rate functions that we can reconstruct, and we have also the boosting transfer function in the model. So those are two aspects that were introduced in JPEG AIC, or well, this joint modeling with boosting was done before by another paper, which I will also explain. And then we have to find out what the trade-off, not the trade-off, but more what are the contributions of these two of these two components of the modeling. That's the content of this little smaller examination. Okay, so the model, the traditional model for image quality reconstruction from comparison is just a pairwise comparison between distorted images. The reference can be shown optionally, then it's a triplet comparison, and that's what we call a plain triplet comparison. So you've seen an example. And so from that, we get one scalar value per image and obtained by Thurstonian reconstructions using maximum likelihood estimation. And this works well also for cases where we have distorted images from different sources. But we are only, we are looking at, of course, compressed images from the same source in different codecs, perhaps. Okay. Then we have these two powerful extensions, namely, we also compare between boosted images that increases the perceptual sensitivity and discrimination power, the visual one, and the functional model for distortion rate function and boosting transfer function. That's the parameterized model that we introduced here. And then we have the joint reconstruction using PTC and BTC together with the functional model. And now here's the ablation study. We want to separate the effects of the ASC3 joint modeling and the functional modeling. And for the method that we apply here is just full simulation, assuming the null hypothesis of a functional model. So not the data set is in the center anymore, but we have the model of some functional model that's hypothesized, and then we'll do the study. Okay, so that was already shown. I don't know. Okay, I pressed the wrong button. Okay, yeah. Okay, so the following taxonomy applies now. So we have, as models, we have the pointwise model and we have the functional model. And then we can have only plain triplet comparisons or only boosted triplet comparisons, and so not a joint model yet. The joint model would be combining plain and boosted triplet comparisons. And so we have these four squares that we can fill or that we can consider. And so the top left square would be the classic Thurstonian case 5 approach, but with modern maximum likelihood estimation. Thurston back then didn't have maximum likelihood 100 years ago, and so they used some regression method using distances. And in 2021, we had this paper in IEEE Access that introduced the boosting idea, and there we aligned it with the plain triplet comparison result using nonlinear regression. And now we can do it also with maximum likelihood estimation. Okay, the ASC3 standard does the joint modeling, including the functional model there, and here the plane reconstructions using a classic method together with the functional model was not done before, I think, but I'm not sure. There are so many papers out there since 100 years ago that I'm not quite sure. Okay, so now going back to the classic Thurstonian case 5, and this is from our old paper from 5 years ago. So we have here one codec type. It's not codec, that's why I put it in quotes. It's motion blur. So we applied motion blur and on 30 distortion levels, and so the last one is about 3 JNDs. And we did the triple comparisons at distortion levels I, J, and K. So we compared I and K and asked which one is closer to J. That was the question there, not always asking about the distance to the source. And okay, so we had these numbers of questions, etc. I don't want to read all the details to you. So now the blue curve here now is the perceived distortion in JND units as we increase the distortion level from 0 to 30. So this is roughly 3 to 4 JNDs here. And it's quite monotonically increasing. Now when we do the boosting with amplification and zooming and flicker, we get the red curve here, right? So it increases much faster, and there's a gain in it that gives us the ratio between the slope of the red curve and the slope of the blue curve. And you can see that this the ratio is usually above 5, so that means the sensitivity has increased by a factor of 5 by means of the boosting. Okay, so that was one of the main findings of this paper there. And then here now we're still in 2021, where we look at the accuracy in terms of true precision rate, true positive rate, the precision in terms of confidence interval, and the rank order correlation that we get here. So here we have on the horizontal axis a distance d that is the difference of the distortion levels between the two compared images left and right. And then here's the true positive rate. So you compare and ask which has the stronger distortion, and then, okay, 0.5 is what you get by guessing, and 0.75 would be a 1 JND. And you can see with the plane triplet comparison, with the plane comparisons, we get here at a difference d of 8, not even 1 JND less. But for the boosted version, we have already 1 JND here between between d equals 1 and 2. So again, this shows that the boosting is very, very effective here in this case. And then we ran computations of a confidence interval. So this is the confidence interval of the impairment, the distortion in JNDs. And the red curve again is for the boosted, and the blue one for the plane triplet comparison. And you can see that the confidence intervals for the boosting are one order of magnitude smaller than the confidence intervals of the plane triplet comparison. So that means we have a lot more precision with the boosting. It really helps the human visual system to identify differences and to quantify it. And we can also look at the SROCC. So we have 30 stimuli, they are all ordered, and then you can calculate the SROC from the reconstructions, and you can see with the boosting, you get, you start with 0.94 and you end up with 1, and the blue curve there is, for plane triplet comparison is well below it. So from this, one can analyze and find out that the value of one boosted triplet comparison compares to 25 plane triplet comparisons. So this is a huge factor. You can save 25 times the money if you use boosted triplet comparison in comparison to plane triplet comparisons. However, there are some limitations to this study. The findings may not be generalized. So most prominently, this comes from the fact that here we are dealing with motion blur motion blur is not compression. Motion blur is a linear operation, and as we increase the parameter, it's just a linear increase. And so this technique is, this is really the easiest possible case that one can hand to this type of analysis. So this is not fair to assume now, this is the result and this will work for other cases as well. It does not. We don't have that. So, but this was the motivation for us to use these techniques. And now, a last slide for this old work. This was what I had before calibration, and now here's the calibration. The blue curve here is how the impairment in J&D is increasing for the boosted scales, and then the others here are for the plain triple comparison. So if we use the plain triple comparisons from only 200 responses, that's the green curve here, we get, this point was reconstruction. And if we take our full data set, 1,360 responses, we get the red curve, which is very, very similar. Okay, and now you can have nonlinear regression from the blue curve to either the red or the green curve, and then we will get the black curve. So that is a reconstructed version, just a scaled version of the boosted one. It's not maximum likelihood estimation, but this is just a nonlinear regression. And so this is what we then submitted as our final result. Okay, you apply boosting, you do the reconstruction, then you do the rescaling with very few plain triple comparisons, and then you get a result that is much more precise as what you have, what you would get with plain triple comparisons with the same budget and we can afford 25 times as many boosted comparisons as plain triple comparisons. So that's this lower part here. Now, okay, let's now go into our simulation. So how do these findings from 5 years ago correspond to what we can get from a simulation with the functional model that we have in ASC 3 that's added on top of the boosting? So here's what we do. We take one source, a codec pair, only one in our simulation. We take a distortion rate function of the exponential type as before. For simplicity, we just take a linear boosting transfer function, h beta. It's just a multiplication by beta. So we say, okay, a boosted perceived distortion of 3 JNDs will be just 1 JND in the plain case when beta is 1/3. Okay, so then we have 30 distortion levels or bit rates as in the previous study. And we do these comparisons I, 0K. So now we compare with the source again, as one should for the ASC 3 study. Then we have a span of 10 levels. So we only compare levels 10 with 11 up to 20. And level 15 is compared with levels 16 up to 25, etc. Of course, it doesn't make so much sense. We think that you compare level 0 with level 30, because then everyone will agree, almost everyone will agree that the level 30 has a stronger distortion. Okay, we can have as many responses as we like in the simulation, of course, and we evaluate the root mean square error using the 30 bit rates with respect to the ground truth distortion rate functions. And when we look at the BTC case, we just divide by this linear boosting factor to normalize things. Then we use averages over 100 or 200 trials. So the first part of the study, we study first the potential of the boosting for a variable linear boosting factor beta. So there's a beta. So for a large beta, beta is the factor that we have to apply to the distortion for the plain comparisons. So I said 1/3, it should be 3. So if we go a factor of 3, we'll multiply the plain distortion by 3 to get to 3 JNDs for the boosted case. So that's the boosting factor. So as that changes, what is the effect? And one can imagine that if for a very, very large boosting factor, things become so trivial that all the answers will be uniform in the sense that when you have a comparison, all the crowd workers will say the right image is the one with the stronger distortion, if beta is only large enough. Okay, so that has to be analyzed a little bit. And then in the second part, we fix the boosting factor to 2, which is what we have measured in our practical experiments in ASC3. And then we can look at the trade-off between PTC, BTC, and study the joint pointwise and the functional models. Okay, so here's the part 1. Accuracy for boosted triplet comparisons depending on beta and the budget. So we also fix a budget, and again we say that a plain triplet comparison has twice the cost of a boosted triplet comparison. So here we only collect boosted triplet comparisons, and we now look at different boosting factors, here going from 0 to 15. So the plain triplet comparison corresponds to the case beta equals 1. Okay, as I said, for root mean square computation, we divide by beta for comparison, and then we average over 100 samples. So on the top left, you have the plain pointwise model, and each curve corresponds to a different budget of plain triplet comparisons. So 500 plain triplet comparisons is the budget for the top curve there, and 8,000 for the bottom curve, the green one. And you can see as the boosting factor increases, our performance in root mean square error, well, the root mean square error gets smaller, so our performance improves, but then it degrades. And that's the effect that when we have a large boosting factor, there's no information anymore in the data that we collect, because everyone agrees, so the right stimulus is the bad one. There's no information in it, or almost none. The entropy is 0. Okay, so yeah, that's on the right you see what happens if we use the functional model, not the plain, just the functional model, and only assess that. And then we have, okay, that with a larger budget, the root mean square error is smaller, and also we have the effect that we increase as we increase the boosting factor to 2, the error decreases, and then it increases, but not as fast as for the pointwise model. Okay, so to further explain this, so okay, we had this decrease here at the initial part, so the boosting improves the root mean square performance for both models, the pointwise and the functional model, when we increase beta from 1, which is the plain triplet comparisons, up to beta around 4, 2, 3, maybe 4. And then if we go from left to right, from the plain pointwise model to the plain functional model, we see that the functional models also improve the performance. The curves on the right are lower than the curves on the left. So the functional model is more powerful than the pointwise reconstruction model. Okay. Okay, now we come to part 2. We want to look at the trade-off of BTC, PTC for the pointwise models. And we have here now root mean square error and correlation. Root mean square error on the left, correlation on the right. So here we fix now our beta. So it's 2 now, so that's fixed. And then we can see how the reconstruction quality in terms of root mean square error is behaving. So the dots here are just for plain triplet comparisons, so the ratio is 1. And you see, of course, for higher budgets, you get a lower RMSE as expected. And also we see that when we start with a small ratio, like only 0.1, we have few plain triplet comparisons and many boosted triplet comparisons. We can improve it by adding a few more plain triplet comparisons, but then the error starts increasing, so we have optimality around 0.2, 0.3 or so for this simulation. And for the correlation, we see that the more boosted comparisons we have, the better the correlation, the larger it is, right? Small PTC means more boosting, or more boosted comparisons. So that's that. All right, so this is then these two cases. All right. Okay, and now the left is the same picture as before. So root mean square error versus the ratio of PTC. And now we have the joint functional model. So where we have included the point by, well, we jointly take the plane and the boosted triple comparisons and apply also the functional model. And there we see a new effect, namely that these curves here now, as we increase the ratio of PTC, they're decreasing and then they are sort of staying at the same level. That means we can choose a PTC ratio larger than 0.2, 0.3, and nothing will change. So this means the functional model, they are equally good, and so they kind of override all the advantages that can be had with the joint pointwise model. So one can conjecture that in this case, in this simulation, assuming the null hypothesis that it does not give a large advantage, or maybe no advantages at all, to look at boosted versions. One can do only just PTC and apply the functional model. The functional model will iron out all the errors or the noise in the PTC data sufficiently. This requires, of course, that our workers behave exactly like the functional model, which is not really the case. So one cannot really conclude for the practice that one should just abolish all the boosted comparisons in order to get the best performance here. Okay, so this is already almost the last slide, the second one. So the conclusion is, under the null hypothesis of the simulation model, the prior of this functional model is very strong, so strong that it fully masks the gains achievable by joint models that includes the boosted stimuli. Right? Here you can see the collection. So here we have here we have a small budget, and here we have a large budget of 1,000 and 8,000 comparisons. And you can see the dashed lines are for the pointwise model, and the solid lines include also the functional model. And of course, that is much better than just the pointwise model. And then when you vary also the ratio of PTC, you see that for the joint models, you have a minimum here between 0.2 and 0.4, but for the functional models, well, there's no clear minimum visible. It's all the same for the large ratios of PTC, and maybe you don't need any PTC in this case anymore. Okay. So then, what is the conclusion in practice? Okay, the prior of the functional model is only approximate, right? It's the results may vary. Further studies are needed. One could use one type of distortion function for the synthetic model, and another one for the reconstruction, for example. Does that bring back advantages of the joint modeling approach is the question. Okay, and then another thing is for some codecs, a functional model may be inappropriate. So for JPEG AI, as mentioned in the last talk, it could be the case that a pointwise model should be preferred. So then that should be used, and then one has to take into account Akaike information criteria to estimate the quality of the model selections, because then you have many more parameters in there, and then it becomes more difficult to judge which model is the better one. Okay, so thank you very much for that, and I think we're well into our time.
Yes. Questions. Are there any questions here or online? Oh, I see there's an online question. Please go ahead. Mohsen?
Oh, okay, only me. Thank you, Dietmar, for this presentation. First, for JPEG AI, I just wanted to mention, nobody here from JPEG AI, that JPEG AI depend to how you create the image. It might have monotonic rate distortion function. So that's the way we sample. we generated the image, it was not monotonic. It's not necessary JPEG AI, it is functioning like that. But related to the talk, this is, I mean, Dietmar, do you think this is also very important that in what distortion level you are evaluating this boosting effect? Because let's say if the distortion level that in the PTC condition is already large, the boosting might not give too much advantage, it might saturate it. And also if it is it's very below, very small distortion level, the advantage it might be also again small there. It could be that the reason. Thank you.
Yes, of course, and this is something that we had already observed in our 21 paper. See this on this plot here, you see the gain curve. The gain curve shows you the effect, the effect of the boosting. How much gain does it give you? And so if the factor is large, there's a lot of gain. And this happens in particular for small distortion ratios. And you said, okay, for large distortion ratios, it's not so clear. And yes, okay, so for large distortion ratios, the gain is smaller. So here it's still at 10, but this is not a typical example. Normally the gain would be much smaller, even less than 2 or so, maybe just 1 even. We had this for other cases, not shown here. So yes, so right, so the technique works best for very small distortions, and this is also the target of ASC3. So lossless to nearly lossless, and maybe just a little lossy cases. So for 3, 4, 5 J&D distortion, we should not expect that the boosting will give us, much of an advantage. So there already ACR might be working well, right? So yes, we could consider, and I think this was also mentioned in one of our JPEG meetings, to apply the boosting only to lower distortions and to make it smaller for larger distortions, or abolish it for larger distortions, which would change, of course, our transformation of the boosting transfer function.
Thank you.
Thank you very much. Can you, for me, it's like super non-intuitive. Why this function is not monotonic, the red curve? Can you elaborate?
Yes, so again, the definition of the gain factor is you take the slope of the red curve and divide it by the slope of the blue curve locally, right? And so here you have a very strong slope. Here you have here you have a very small slope on the blue curve and a normal slope for the red curve, and then you get these factors 15, 20, 30 or so. And here the blue curve is steeper and the red curve is not quite so steep. So that's why this is where you have a minimum here and then it increases again a little bit.
Okay. Well, you can take it offline.
Yeah.
I'm still fully
Yes. So the point that Mohsen mentioned, when you have high distortions, you see it already very well without any boosting.
Yeah, exactly.
And with the boosting, there's some kind of saturation also taking into effect, right?
So that is why, for me, the gain should be low.
Yes, yes.
Going down to 1 even, yeah?
Yes, we have seen this also in other cases, not here. Mm-hmm.
I'm wondering how if you are sure that the boosting, that you can use boosting for different distortions, the same kind of boosting will work the same way, because you assume that boosting gives you a certain gain. There is a certain function, and this is like well studied in this case, I understand, because you did the whole experiment. But do you have any feelings like how it generates to very different distortions?
Yes, I can give you some information about this. When we started out the study, the reconstructions with the boosting transform function, my first approach was to use the same boosting function for all types of distortions. So we have one source and 6 codecs, they have different distortions. JPEG AI has some distortions, and JPEG, the classic JPEG has other distortions and so on. But I try to have just one transformation, like 0.5 times x plus or minus 0.1 times x squared, or something like this, okay? And find the parameters optimally. And then I applied this, and it did not work very well. We had very large errors, and that indicated that the different codecs that give us different types of distortions translate to different transfer functions. And so we expanded the model by introducing more parameters and having one boosting transfer function per codec, per distortion type. So you're perfectly right, and it's necessary to take that into consideration. But we did not quantify or conduct an experiment to sort of isolate this effect and quantify it and so on. That we didn't do. We only had this one study where we applied the same distortion to, or the same boosting to all the stimuli, and then we found that, okay, we have to use different boosting transfer functions. Maybe you can do some research to find out how to change the distortions of all the codecs so that at the end you have the same distortion, the same boosting transfer function for all the codecs. But I think that's not a useful suggestion.
Thank you very much. So it's also clarified my other question that could we reverse, like find the boosting that is really kind of easy to see the distortion, yeah? So like changing the beta instead of changing the different distortion levels. Yeah, but I understand it doesn't make sense in this case because it would be slightly different for different codecs, so it's not super fair comparison that back then. Okay, any other questions?
One comment regarding what you asked, that Dietmar shared with you, objectively evaluated the different the transfer function in different codec and different source image and so on, very large data set. It is the transfer function, it might even depend also on the source somehow, but mostly based on the codec. And the different codec might behave differently, yes.
Okay, thank you.
Thank you.
All right, we are at the end of the session, so seeing no questions, we can have coffee on time. Ah, now it's photo? Okay. Ah, but you was behind I thought you are not in the room.
Always somewhere near.
So photo with online or without online people?
Yeah, it's about social events, so unfortunately.
No, but the photo. Take a photo of this.
Yeah.
With online, definitely.
So we start from the photo.
Yeah, we start.
Yeah.
The people online want to turn on their camera and we take a picture. They will take and look sometime.
So not like putting the online people here and we standing here and to. We can do it like that.
Yeah. Again.
All right.
Let's at least grab people who are online right now, so don't lose them.
Yeah.
Find the Zoom.
So if
Online
people
people?
online are willing to turn on cameras, we could try to grab the photo. No, because I do. The big question is, are we trying to do the photo all together? So we are physically here and they are virtually?
I believe that it's very difficult to put all of us physically.
Uh-huh.
But there is tools to do that. As long as you can grab right now the ones that are online.
Yeah.
We can take another one upstairs and we can combine
Yeah.
the two. It's my
Okay.
suggestion.
Yeah.
Not to make the discussion easy.
Good idea.
You may want to help with Then AI too.
Yeah, and then. Yeah, but every participant then had to rate it, yeah? If we use Gen AI. Data set and.
Okay, perfect. But I just don't. Okay, view, gallery.
So for online people, the idea is now is the time for you to turn on the camera
Yeah.
so we can take a screenshot of you and then combine your screenshot with our photo in real life.
Right. Who is
Yeah,
taking the
yeah.
screenshot?
Can you do that? Yeah, I think that's fine. So smile.
Is there any tool in like Zoom, right? You go to gallery mode. You go to view for more. Go to view to the left more. Go up. Gallery.
So you can take a break from smiling.
Gallery, you only have half of the people. There is a large gallery. Gallery size. Gallery, now go to gallery size. It's not. You need to pay money, I guess. This would be, but still, still, I don't know how to.
What do you want?
It's like
a small cell. Yesterday, the people used.
Can you make a photo from the Teams? Because it would be better quality probably than from the screen. That's the print screen. Yeah. So I did the print screen. We can.
Are you sure you take it?
Fourth person. There was a fourth person. Sorry, could you turn on camera again? So we will do another screenshot. Just. Okay. Yeah. Now we've got even 5 people.
Perfect.
Perfect.
Now it's time for smile.
Smile, take.
And now.
Now let's go for the physical. Yeah. Okay, so thank you very much. We will have still 15 minutes break from.
Thank you very much.
Yeah. Just for the people online, because the announcement right now is just for people that are physically here. Interesting.
Just one question: that our slide, we should send it to you, or we can share them from our PC or laptop?
You can share it from your, and I will just move it on the screen in the room.
Thank you.
This is not the screen.
Ah, yeah. Also, that's why it's.
But we are not sharing anything on Teams either. So.
Yeah, I was, and I. Give me a second. Okay, so about the social event today, we meet at 7 p.m. in Hotel Forum, and it's the last chance to fill the menu that you would like to eat today. If you didn't do that before, this is the last call. Yeah, so if you don't do that now, I cannot make a reservation for you. So this is the QR code for like 2 dishes to be chosen. And for the payments, you did a really good job. Only 3 people didn't pay me yet, so I think it's a good score. So this information is also in email that you got from Mateusz. So it is there if you need it, but also you can ask me for that. And the venue itself is like 20 minutes from here or 25 minutes by public transportation. It's called Panorama Forum. So you can see it's near the Vistula River. So this is what you would like to look for when you will be heading there for 7 p.m. dinner. And the entrance is this tall part. So the elevator is here. You have to enter here. So there is only one small elevator. So it probably would be wise to be a bit earlier to, you know, like have some rounds in terms of taking the elevator. I don't think so. I'm not sure where is the staircase. Yeah. I only use the elevator, and I think staircase is in a main building, but this is the main entrance to the restaurant. So I guess in terms of fire, there is some staircase, but like you should take the elevator otherwise. So yeah, that's it. That's the end of. No, but maybe I'm fortunate not to see that before this evening. Okay, thank you.
Okay, so we are back in 10 minutes for the rest of the SUM session. So MOSFET. So we will start from Bartek presentation. It's not long, and then we will switch to yours. Okay.
Yeah, sure. I'm expecting that you're following the schedule, right? Thank you.
Okay, since between this session and is the end, and then the social. So let us try to start on time. So we are left with 3 presentations. First is given by Bartek. He's my PhD student, and it's a tiny topic that we come up with with modeling that hopefully will be important for the group if we start to analyze also per comparison, stuff like that. So we hope to make a small clarification about it. So Bartek, the floor is yours.
Thank you very much.
My name is Bartek. As Lucian mentioned, I'm a PhD student at our university. And today I want to talk a little bit about two methods to calculate p-values in g-test mentioned in presentation, in Dietmar presentation. These results partially based on our joint work with Lucian, Dietmar, and with my other PhD supervisor, Bogdan Ćmiel. Let's start with some context. Let's imagine that we have some subjective experiment, and from this subjective experiment we have discrete data. So for one PVS, we have a count for each PVS, like here in this example, 5 ones, 6 twos, and so on. Total number for grab your attention, let be 24, and we want to model this data. Someone can ask me why we want to model it and feed the model, like here, for example, normal distribution. And answer is, let's imagine we have two codecs, codec A and B, and we have some picture, some multimedia, and there is some distortion from codec A and codec B, and we can calculate. And we so we have some pair of two PVSs with some distortion, the same picture with the same bit rate, and we have two means. Means I mean the average of ratings. And we want to compare these two means between themselves. So the better means that the codec, this codec is better, but we need to find out whether these two means are significant different. So we need to conduct some statistical tests. Of course, there are a lot of tests like T-students, but those statistical tests have some assumptions like normality or performance very poor for small data sets. So the idea is if we really sure that our data comes from a particular distribution like normal, we can compute directly prepared based on that assumption that our data comes from particular model. We can prepare a more powerful test to do that with this particular assumption, true assumption about our data. So let's return to this graph. So we need to validate if our data comes from here normal distribution. To test it, we need to compare observed probabilities like P1 to P5 with those predicted by model. We can do this using G-statistics, like in the form you can see on the slide. And the one important thing regarding this statistic is it has asymptotic chi-square distribution with some degree of freedom. In our case, is 2 degrees of freedom. But the distribution is only asymptotically. So what this means? It means that for a large sample, the distribution of G-statistics behaves very similar to chi-square distribution with 2 degrees of freedom. So based on that, we can calculate some p-value, and based on this p-value, we reject or not reject the hypothesis. Yeah, if it comes to hypothesis, we have null hypothesis that our data comes from the normal distribution, and alternative is it doesn't. So The key part of this presentation is to decide whether method should be used to calculate this p-value. So we have some option to do that. For example, we can compute it by using an asymptotic distribution. It's a very fast method, but asymptotic. So for small sample size, like in HGTV, where we have 24 responses for one PVS, it's rather poor for such sample, and moreover, in these results, there are some empty categories in these responses. For example, we don't have any one rating. Or two, and so on. The next method is a method based on bootstrap. So we calculate the empirical distribution. We determine the empirical distribution of our G statistics. So we replicate, for example, 10,000 times the same procedure, and we get the empirical distribution of our G statistic, which is close to the truth. To the true state. We have two methods based on Bootstrap. The first one is described in Wishman and Hill paper with respect to some psychometric function. It's relatively fast to calculate, but it doesn't take into account the fact that we don't know the parameters in our distribution. If the parameters of distribution, the true parameters of distribution, for example, from the hypothesis normal with 0, 1, it'd be good, but we usually, in general, we don't know this parameter, so we need to estimate it. And here is the moment when the Bootstrap described in Davison-Hinckley comes in. It's very time-consuming method, but for each iteration we refitting the parameter. So we replicate the same procedure 10,000 times, and because of that, it's really properly calibrated method. And for this reason, we just consider the asymptotic one and Bootstrap, then the last one to compare these two methods. Here, where is the problem with asymptotic distribution? You can see here the empirical cumulative distribution function. This is a blue curve, and the theoretical one. The important thing is that the distance between those two cumulative distribution function is very large, and it's really impact on the p-value calculated from this distribution. Of course, I need to stress it out. Empirical cumulative distribution function is closer to our true state. Theoretical one is only asymptotic. How can we compare these two methods? And the one most popular way to do that is calculate significance level for when we assume that the null hypothesis is true. Let's grab our attention to the first example. Like we assume that our data comes from normal distribution with mean 3.5 and variance 0.36, and based on some we quantized the normal distribution, and we can we calculate the probabilities from this model because the density is known from this distribution, and we can calculate from this distribution, we can draw 10,000 samples. And for each samples, we calculate p-value using asymptotic method and using a Bootstrap method. And here we can see that here is the theoretical significance level under the true hypothesis, and here is a obtained using a asymptotic distribution, and here by Bootstrap method. And the important thing is that Bootstrap holds a significance level. These values are very close to the theoretical one, but for asymptotic is twice or more than twice lower than Bootstrap, and it's just performance very poor when we have a when we have a sample with, for example, empty cells or with a small sample size. Here is some comparison. You can see that the Bootstrap values and asymptotic is relatively low than theoretical one, but there is no mistake. Everything is okay. Because here, as you can see, we have a true distribution. Very consists of 3 ratings. The probability for 1s and 2 is practically 0, and normal distribution behaves in such situations very good, because it fits very well to 3 cells. So it's a case from the middle of the hypothesis, and test it's really hard to reject it by test, because this case is typical from this distribution. So it's really okay. Okay, so let's go to the real data. I used HGTV data set. Here we have 6 sub data sets. And on x-axis we have asymptotic p-values, and y-axis is Bootstrap p-values. So each point from on each plot means the first value is asymptotic p-value and the second one is Bootstrap p-value, and for each PVS. So there are number of points of each plot equals the number of PVS in each subset. And yeah, and you can see that the p-values are relatively p-values for asymptotic approach are relatively bigger than those for Bootstrap p-value, and yeah, it can be because asymptotic p-values based on this asymptotic distribution, which is not proper for small samples. But the real interesting case are when we just zoom it and look only on those points, on those cases, when the Bootstrap approach reject the null hypothesis, so p-value is less than 5%. But asymptotic p-values says completely different story. Like the p-value is, there is no reason to reject null hypothesis because p-value is more than the assumed asymptotic level. And here is some cases, but let's grab attention to this one. So 0 1s, 2 2s, or 3 7 3s, and 15 4s. And you can see here this empirical, the blue curve is empirical cumulative distribution for G statistics. Theoretical one is dashed red curve, and we have two. On the green is G statistics observed based on this data, and we have 2 critical value for G statistics. So on the right, from the yellow line, yellow dashed line, we have a rejection region for the Bootstrap method, and on the right, from the pink one, pink dashed lines, is the rejection region for asymptotic approach. And it can be observed that our observed G statistic value is in the rejection regions from the bootstrap, but not in the rejection regions in asymptotic approach. So that's why the asymptotic approach says, okay, we don't have a reason to reject this null hypothesis, but the bootstrap says different story. They reject the null hypothesis, and yeah, because the empirical GTS distribution is closer to the truth, to the close to the truth state in our data. Yeah, and that's it. Thank you for your attention. Here is some bibliography, and if you have any questions, I'm glad to answer it.
Yes, Oscar, please ask your question. No. So this was not the hands.
Hello, sorry.
Okay.
Thank you very much for the presentation. Actually, we did some analysis in this, comparing these two for the RFC paper for extended not sure option study that we did. And with Dietmar, we had a different approach for bootstrapping. For example, I think Dietmar was fitting a function and then sampling from the function, but I bootstrap the data itself. Which method you are using for bootstrapping right now? You mentioned it, but I don't recall which one it is. How you did the bootstrapping here?
Yeah, here for bootstrapping, we use those one, Davidson-Hinckley bootstrap. So it's we make some repetition, for example, 10,000 times, but we fit the fit the distribution. So we refit the parameter for each time. So once again, we draw 10,000 samples from fitted distribution, and for this 10,000 samples, we refit the model for each sample and calculate the G statistic in this way.
Yeah, thank you. That is, I did the same way that you explaining, but I think Dietmar, you did it a different way, that you fit one model to all data and you sample several times, and then you look to the actual data if it is within 95 confidence interval of that or not, right?
I think what you said, you sampled from the model, right? So you have
you sampled from the model. Your method you sampled from the model like 10,000 times, and then you look to the actual data if it is fall within 95 confidence interval of that sample with one model that you fitted to the whole data. But myself, I did it as he did right now, he explained. So I always fitting again and again. So that's the difference, right?
But Mosen, you sampled from the data and he sampled from the model, the Gaussian model, right?
Okay, so he doing it like what you suggested, you used. That I will always criticize it. But okay, so he did advise. I think this is different when you sample from you have, let's say, 1,000 data. You sample always for each bootstrap sample, you sample the actual data and you fit a function and you calculate the whatever you are looking for, a statistic that you are looking for. And then you do this 10,000 times, or if you fit one model to whole data and then you sample this model, you sample the model itself 10,000 times or whatever, and then you look to actual data fit with 95 confidence interval. Can you please clarify if you're using the first approach I have explained or the second one?
Yeah, so maybe I just describe the way I can use this bootstrap Davidson-Hinckley. So I have some sample, like here is from the, and yeah, here. So 0 to 7, 15, 0. and I calculate for this sample. I just fit the normal model. So using a maximum likelihood, we fit these two parameters, and based on this model, we using some threshold. I just showed on the previous slides. So we obtain some vector of probabilities, like here, and we draw from this fitted probability 10,000 samples, and for each samples we do exactly the same. So again, we use a maximum likelihood, and we obtain two parameters. Yeah, so maybe like E here. And for such parameter, I calculate, of course, at the beginning here we have G observe statistics. So it's the value of G statistic related to sample. But here we have a bootstrap. We have 10,000 samples. For each samples we do exactly the same. So we fit the, based on maximum likelihood, we obtain two parameters. Again, quantize it based on some thresholds, and we calculate G statistics, like some version of G statistics. And based on that, we have some distributions of G statistics, and using these distributions, we just can calculate p-value using a bootstrap, like how many these values exceeds these values. Yeah.
I understand the method that you use, the method that Dietmar suggests, the way Dietmar using it. So this is, in my opinion, has some limitation that, for example, if you can increase the sample size, and otherwise, when you sample from normal distribution with after a sample size increase, you get the same distribution again if you fit a distribution to that data sampled from theoretical distribution. So this is some limitation, in my opinion. We discussed a lot with Dietmar about this, but I think I fully understand right now what you did. Thank you.
Mm-hmm. Yeah, it's time consuming because we need to refit 10,000 times.
Yeah, but in my opinion, it's better to use.
Okay. Sorry.
To sample the data and then to fit the distribution to the data and to look at the statistic of the refitted distribution to the sample data, not to a theoretical model, sample from theoretical model.
Yeah, exactly. I understand now.
Yeah, thank you.
But because I really sorry to take so much time, but I really want to understand. So your idea is to generate here a new sample, and this will be done 10,000 times. Yeah, the sample will be a bootstrap of this sample. So in general, we have 0, 0 here for sure, and then some numbers here depending on the bootstrap, and then we estimate here our new me J, let's say, and sigma J, yes, and from there we calculate the G statistics, yeah?
Yes, I mean the point is when you have a theoretical model, when you sample the theoretical model, I understand what is in behind this. That you said, okay.
No, but no, sorry. I'm sorry to cut. But I just want to understand: is the way you want to do it, or you do it?
I sample. Let's say we have 1,000 sample or 200 sample of data. Okay, you fit.
So this is data.
Yeah.
I sample it.
If you say data, I don't see anything here right now if you are using a mouse or whatever. But you have the data, you sample the data, you fit a distribution to it, okay? You get, for example, the GND. You estimate the GND or mean value or whatever. And you can sample the data itself and fit a model 1,000 times or 10,000 times. You get a distribution that you can compare that one, see if this is statistically, then you compare that data with the actual data, if it is fit with 95% confidence interval of that distribution. But
okay, so Peter, you are not here because it's kind of difficult to decide. But in my opinion, if this is done this way, this is wrong, and I see a clear reason.
Yeah, the parametric sampling.
Yeah, so this is different discussion, yeah.
Yeah, it is not parametric sampling. That's what I mean. The parametric sampling, if you increase the sample size, otherwise, for example, there is some theoretical reasoning for that. For example, if sample more than 50 sample is often, you get very good close to the theoretical distribution. So if you have a normal distribution and say you sample it, let's say more than 50 sample or something, you're almost getting the same parameter again.
No. But just look, if you get a very good sample here, then and this sample is large enough. Okay, no, really, we have to take it offline. Let's try to make a call. True. Yeah, because we have to go forward.
I mean, we have with Dietmar, we talked about it. We have a paper. It is 2 years ago, it's written, still not published, but we discussed about this a lot in different model of this analysis using theoretical and different bootstrapping method.
Yeah, sounds like a perfect thing to do for some session or even a separate call.
Yeah.
Okay, thank you very much for all the doubts, and I love to discuss it. But we have to go forward to, by the way, to your presentation.
Yeah, okay, thank you. Should I share my
Yes, please.
If you stop sharing, please. I cannot share. It seems I have no permission to share right now.
Are you sure that it is,
Well, I pressed show sharing, and I cannot select anything here.
But it might be like on your side, actually.
Okay, maybe I have to, okay, yeah, okay. Do you see right now the file? Do you see the slides?
I could see it for a second, and now I cannot see it anymore.
No, I will change it. It's okay. So you will change it.
Do you see it right now, or?
Well, it's actually all black.
Now it's black.
Okay, I maximized the browser.
Now it's okay.
Okay, so should not be in full screen mode.
Just play it as it is.
Okay, thank you. Hello, everyone. My name is Mohsen Janadele, researcher from University of Constance, together with John Snayer from Cloudinary and the chair of JPEG AIC. We will present our work on large-scale dataset for fine-grained assessment of image coding. Currently being developed with the JPEG AIC activity. This work is also part of my DFG project. AIC4 focuses, Dietmar explained JPEG AIC3, and also he mentioned about the JPEG AIC4 activity. JPEG AIC4 focuses on the evaluation and development of objective image quality metric for compression distortion, especially in the high quality to lossless range. This work is motivated by the need for reliable fine-grained evaluation across modern image codec, including both conventional and learning-based codec. This is particularly important in the high quality range, where visual quality differences are subtle but still very relevant for some application and for codec development, for perceptual optimization and metric development. Existing image quality datasets are limited in codec diversity, especially for learning-based codec, as well as source image diversity and fine-grained distortion coverage. Our goal is to build a reproducible, large-scale, and diverse data set that support fine-grained evaluation of compression artifacts produced by modern image codec, including both conventional and learning-based codec. The paper for this paper is still is not submitted, so your feedback will be greatly appreciated. We named this dataset AIC 226. So the dataset contains 70 source images selected from nearly 3,000 pristine image candidates that were that the resolution of them is 840 by 944 to 4K resolution. Source image selection combines semantic cluster. We cluster this image, 3,000 image with semantic clustering feature. And then objective metric disagreement was used. So half of this data, it was selected by the to maximize the diversity, half of the source image to maximize the metric disagreement. The data set then was encoded with 17 codec or codec configuration, including 12 conventional codec and 5 learning-based codecs. And nearly 10,000 compressed image, and for each source codec, about 20 approximately uniform perceptual distortion level was chosen using CVBDP mapped to JND. The dataset will be publicly available. So the existing dataset, as you can see here, they have usually only include 1 or 2 codecs, and the resolution often is fixed resolution, or so in here we have very large diverse of the source codecs, like 50 sources that they are all piston, the source image, all include all full EXIF data, and with all capture information, and the image are encoded with 17 codec, as you can see here. So the source image were collected from a volunteer contributor photographer with different camera, and also from some public repository, and also